Hi guys, hope everybody is fine. So welcome again. On our last video, we talked about like why we need the linear algebra, right? So as you remember already, so this there we just little bit of recap. Like we showed like okay, if we have like this axis x and y, and we have some different types of points over there or some kind of elements into that axis, and the question was how can we divide it. We told for two-dimensional we can divide it by drawing a simple straight line like this, and when it is a three-dimensional case, and in that case we could draw by we could divide these lines by drawing a plane, right? So these things are related to the linear algebra. So today we'll give a small recap of that thing again in much more detailed way. So points these are points, right? So let's talk about the points today. Okay, so what are the points and how we can draw these things into the axis. So suppose we have this axis x and y. So let's say this x-axis we can tell x1 axis, and this y-axis we can tell x2 axis. So for three-dimensional case, very similarly we can tell this x1 axis, x2 axis, x3 axis. Okay, and these are the centers. Okay, so suppose in this two-dimensional case we have a point P over here. Okay, so suppose P is 1 1. Okay, so that means from x direction we go 1 unit, and from y direction we go also 1 unit, right? So this is the P of 1 1. So 1 defines the x position and y position, and for our new graph we can tell this is x1 and this is x2. So in that way we can write P as 1 1. So P is here a vector representation. Okay, so P, what we are telling this as a vector representation. Okay, very similarly for three-dimensional case, if we have a point here, suppose P1 1 1 1, so because we have like three axes over here, so one point can be described through 3 points like x, y and z. X, y and z. Instead of x, y, z, we are telling here x1, x2 and x3. So how can we define this point? You can define this point p1 as a vector. This vector is 1 1 1. What does this mean? This is our x1 component, this is our x2 component, and this is our x3 component. So like that way we can extend this thing till n-dimensional space. N-dimensional space. So one point can be described through a vector with n dimensions, right? Suppose I have n dimensions. Okay, n dimensions. So to describe a point into n dimensions, how many components we will be needing? We will be needing n number of components. So here two dimension we needed two components. Here three dimensional cases we needed three components, and for n dimensional cases we need n components, right? So P of n we can write like this: x1, x2, x3 till x of n. Okay, so this is pretty much the basic of the dimensional cases. Okay, now let's move to some other thing. Okay, so this now we will talk about like how can we calculate the distance. Okay, so distance of a point from the origin, first part. Okay, distance of a point from origin. Okay, so how can we calculate the distance of a point from origin? Suppose So this is my x1, this is my x2. As already we have told, we will decide this thing as x1, x2, and we are telling, okay, here is our point P. So x1 component we can write like A, and y1 component, suppose this is B. So in the x1 axis we went till how much? A, and in y2 axis we go till how much? B. So that's how we can create this P of AB, right? So x1 axis. So now the point is, this is my origin, okay, O. So from P to O, this is my distance I want to calculate. So how can I calculate this distance? So the formula of calculating this distance is a square plus b square root over. So this is basically simple Pythagorean Pythagoras theorem. Okay, so what is these basically, right? Suppose if we can now consider this part. Okay, let's consider this part only. So let's draw this like this way. Okay, so here if you see very closely, this is a triangle. Okay, this is A, this is B, so and this is our D. So this D square is equivalent to A square plus B square. So in that case, what will be D? Root over A square plus B square, right? In more extended way, okay, in little bit extended way, we can tell one thing. Here we can explain this thing in a little bit elaborate way. Okay, how? Let's see how. Okay, sorry to, okay, yeah. So suppose this is my origin. So origin point, what is the x1 and x2 component? As I am considering about two dimensions, so we have only two components for origin, 0 0. Okay, so from 0 we drew this line x, and from 0 we drew this line y. So instead of x and y, what will tell? X1 and x2. And suppose here is my point P is A comma B. Okay, so this is my distance, and this is my B, this is my A. So another way of thinking about this is how? Okay, just wait a moment. So from these 2 points, this is, I mean, bigger than O, right? We can tell. So bigger or lesser, that doesn't matter. So we want to calculate the distance of P from O, origin, right? So this x1 component here is A, right? So we wrote A. Then the x1 component of origin is how much? 0. So we wrote 0. Then according to the formula, what we know? A square. So this distance we calculate and give square plus B. This is the x2 component, right? And this is also the x2 component, right? So the x2 of P point, right? So B minus 0 square, as the formula told us, B square, right? So we wrote in that way, and then we will do the root over, right? So in that case, the D will be how much? I mean what? A square plus B square. As simple as that. So now if someone come and tell me, okay, I have a different point called Q. Okay, so the Q they are representing as maybe, suppose okay, let me see, M and N. So this Q point, and they are asking, am I the distance of P and Q, right? This distance they are asking. I am denoting as D1, as I denoted this as D. So what will be the distance of this D1? D1 will be, here x1 is following the same formula, is A, and minus M, okay, square plus this is B minus what? N square, and at the end of the day it's a root. So all these thing we are covering from 2D space. Okay, this is how we can define the distance. So for 3D space, what we'll do, 3D space, very simple, okay. So very similar as well, x1, x2, x3, as we told, any point, as it is three-dimensional space, so any point in three dimension, how many components it will hold, x1, x2, x3, three components. This vector will hold how many points, 3 points, right? So another point, if we consider here q, again same, how much component it will hold, three components. Let's say we're telling this x1, x2, x3 prime, every cases. So how can we calculate the distance now about these 2 points? Okay, this distance, how can we calculate? Okay, no need to give the, okay, so the distance we can calculate very easily by extending the previous formula. How? So the main idea is, every cases component wise subtraction will do. This component, first component of p minus first component of q. So you know, from which to which doesn't matter, because if it comes negative also, we are giving it a square, so ultimately it is going to be cancelled out. Not cancelled out, actually it won't matter, right? So x2 minus x2 prime square plus x3 minus x3 prime square, and at the end it's a root, right? So this is how we can calculate the distances of this thing. So is there any easier way of writing this expression, right? Suppose I have like n points, right? So in that case, how can I write this thing? So let's see if we can tell this thing in a very simpler way. Suppose I have a point p is suppose a1, a2, a3, an vector p. This is n dimensional space, as I am telling, n, right? N dimension. And q is how much? Suppose b1, b2, b3 bn. So how can I write the distance? How? Very simple, a1 minus b1 square plus a2 minus b2 square, till will go till n, right? N minus bn square will go till n, right? So this thing, very simply, how can we write in a elaborate mathematical notation? The notation usually we come across to the research papers whenever the professors used to teach us into the higher studies. How? So this d we can write in this way. First we gave the root, so we can tell easily square root. In short, we can write sqrt, square root. Okay, then what, we are taking like a square root of some summation of the summation we are taking, right? Summation of points, right? Suppose p has a1, so I am writing a b minus, now a is traversing from 1 to n, right? So I am giving here I am giving here I, and every time I1, a1 minus b1, okay, then 2, a2 minus b2, then whole square, right? And then every time we are calculating the summation, so we are giving a sum sign, summation operator, and I equal to 1 to n. So this is very simple as that. Okay, this is how we can write the distance, and few more things, okay, that is like we already told here. So a point p, right? So p we can like define it as three components, x1, x2, x3. So this thing we can tell as a row vector. Okay, this thing we can tell as a row vector. So in mathematical notation, as I have like three components over here, we can tell like 1 into 3. So what is 1? 1 is how many row I have, okay, and 3 is how many column I have. Okay, so this portion defined as row, this portion defined as column. So what about this? This is suppose a vector. Here I have x1, x2 and x3. So how can I define this thing? How can I 3 into 1? That means I have 3 rows and 1 column. Okay, so when I have only 1 column like this, then I am telling it as a column vector. Okay, column vector, and this is a row vector. So easily a row vector I can convert to a column vector, and a column vector I can convert it into row vector. How can I do it? By transposing the matrix. Okay, I will talk about the transpose later on, but if suppose I have a matrix like this: x1, x2, x3, x4, x5, x6, x7, x8, x9, how can I write this matrix? So this is my column and this is my row, right? So row number, suppose row is, I have n row and I have m column. Okay, so this is a m into n, what then it will be turned as a matrix. Everything is a matrix. Okay, so thank you guys. We'll talk on the next video. See you soon.